Hey guys, thanks for man, already 17 people and haven't even started. That's awesome. So this is obviously a topic that people are pretty interested in. That's great. Um, so one thing, um, hang on. Okay, sweet. Man, everyone's waiting. So I don't want to start going into the actual project and everything right now. I just want to wait till more people get in. How's it going, GN? Hang on. For the live stream over recorded episode, the recorded episode makes me think of a max. Well, I'm glad you like the live streams. Hey, Mickey. Hey, Bradley. David. So one thing I've purposefully done with this project so far is I haven't really looked into, other than the obviously the video on the data sheet. I haven't really gone through a ton with this, so I don't really have a huge idea of where we're gonna go with this. Um, I've totally saved your project. Awesome. Well, that's fantastic. That's the goal. How's it going? CFXS compressed soup. Now that's a name. Um, so I really, like I said, I don't have a huge thought on what all is going to happen in this, other than it's going to be an evaluation board with this IC. So what I am roughly thinking is I'm using the actually I guess here. Let me, for people who haven't don't know a ton about it. So this is the same. Hey, Paul. So this is the same part that was in the datasheet video I just did. So it's basically it's a brand new part. It just showed up on DigiKey. So even the put 30 volts in, 30 amps, 12 volts. Oh man, you can totally do that. Datasheet video is spot on. Awesome. How's it going, Brandon? Hey, Paul. Um, so yeah, like I said, brand new March, and it's super cool. Like it's one of the coolest buck regulators I've seen in a while. It has a ton of configuration over I squared C, and obviously it still has like the bootstrap pins or whatever they call it. So you don't have to use I squared C if you don't want to, but that kind of defeats the purpose for the evaluation board. So definitely planning on breaking out the I squared C, and it handles up to 40 amps, which is madness. But the one that I chose just for this one is the oh crap, forget the wrong KiCad. So the one I chose was the 453. So the 3 indicates it's the 15 amp version, and I figured that should be fine for this. So what, and also it has this neat voltage sense. I've heard of them doing it lately, but I've never seen it done. So it just directly samples on the output side instead of needing like a feedback pin, which is, or a feedback voltage divider, which is really cool. They say it offers a faster and more accurate correction, which they talk about all in here. But ultimately, and here's how it's done. They sample it on a couple op amps, which is kind of funny thinking about. I'm surprised you don't see this more often. It's probably more expensive because you're dealing with a smaller differential here rather than breaking it down with a voltage ramp, which is cool, or a divider. Hey, Alicio. It's been a while since I've seen you here. Welcome back. Singing. Oh, for sure. I mean, they kind of already are the future right now, it looks like. So that's the gist of it. And what's funny is I was forget who I was talking to, someone in the voice chat in Discord, which if you haven't already, check out for sure Discord. It links in the description. Um, but what was funny is as I was literally writing the datasheet or recording the datasheet video, I realized that there are two pins on this board, or on this IC, GH and GL, which if you look in the application circuit, they are not shown there. And right here, low side MOSFET gate monitor and high side gate monitor. And if you look in search in the entire thing, other than showing there, oh man, I need to have it only find that. But anyway, it doesn't talk about it a single time. So it's kind of funny how I'm writing a video and a blog about how to read a datasheet, and the first datasheet I pick, it doesn't mention two pins on the board. So what I'm assuming those are is all it is you have probably a output that just ties right in here, or one of these two, or from the op amp side. So it's just used to monitor. And one thing, battery management chips are getting really nice. Yes, for sure. Having that I2C is awesome. How's it going, Intermit? Welcome back. So what's cool that I did not know that Vishay had is they have they copied from TI, like the Webench. They have a example schematic or simulation software also, and it shows just the GL pin not connected. So I'm assuming that's fine for the whatever the pins I was just saying, GH and GL. So I'm just going to keep those floating because we don't care to monitor it, or maybe just throw on a test point. So that is pretty much just kind of the overview. Hey, dude, can't. Sorry to hear that, Daniel. Well, we will miss you. I'll catch you later. So what I am thinking is for the evaluation board, obviously we'll have our input coming in. This is good up to 20 volts, so it'll be nominal. I'm thinking like 12 to 15 volts, but really anything probably 10 to 20 works. So we'll have that input here. We can have some sort of minor filtering. I don't think we need to go crazy for this just because it's just a breakout. On the one side, we'll have power coming in. The other side will have our output power. And then maybe we also just blindly break out all of the I2C pins. And then for the VSET, so the VSET pin is obviously VSET ADC. That's very descriptive. VSET is how you set the output voltage. So I'm thinking, actually, I don't know. What do you guys think? We could put a 1K resistor fixed, and then in series with like a potentiometer. So if we did like a 10K potentiometer something and had the 1K in series with it, you could just take a screwdriver and adjust the voltage anywhere on this range. Or we could have it fixed to 5 volts. From what the power designer said, it wasn't very efficient at anything below 5 volts. So maybe we would want to clamp it at 5 volts. I don't know. It doesn't really, I don't have a huge input on it. What do you guys think? Do we want the output adjustable with a potentiometer? And then are you guys fine with just breaking out the I2C? We can break out the P good, break out the enable, and also maybe have it in a jumper. And then there was one other thing, but I forget what that was. Page 8 of the data sheet. Yes, and that's what I was trying to find. They mentioned GH in one sentence. Where was it? Yes, GH. So yeah, it's like what I was saying. It's just monitors this monitors the high side, and like you said, I'm assuming that it does the same on the low side. So that's why I'm just not gonna populate them. I don't think that people really care. Adjustable, break out the pins. I think 1 volt, 12 volt standard power. Okay, breakout it is. Figure 7. Yep, saw it. Oh, I cannot pronounce that name, but I pronounced the aliens. All right, awesome. Yeah, and all these videos, the live streams get automatically recorded, so if you can't catch the whole thing, it'll be up right after. So yeah, I guess let's just start. So what I'm gonna do is I'm just gonna have this on my other screen. Can't the output be set? Yes, it can be. But the goal with this, and you guys correct me if this isn't what you're thinking, since all of this can be done without using the I squared C, I was figuring we could also have it hard coded on here to set the voltage and all of that, or else you'd be forced to use I squared C. Um, it only samples the V set during startup. I have no idea. That could be true. If that's the case, then we could still have it adjustable. It's just you would have to either cycle enable or cycle the power. Like I said, I haven't looked at the data sheet much other than just for the video, so I kind of wanted to go into it somewhat blind. Yeah, I learned my lesson from the USB hub, but at least this one is much more contained. There's only so much that can get crazy on here. So yeah, I guess let me know, since we do have the ability, and I'll pull this up. So we do have the ability in the I squared C side. We can set on off configuration. I wish they had a summary of what was configurable. So we can set the output voltage, trim, presumably if it's offset from like a load. So if you're, and that's really cool that they have that. So if you're driving a load here and it's a 8 amp load and it's causing this rail to sag, you can offset it by a few millivolts or a volt. So it'll be outputting, say, 10, or what would make sense? It would be outputting 6 volts when you want 10 volts here because it's drawing so much. So that's pretty neat. The out margin high, low, no idea. Frequency switch. Oh, so you can adjust, obviously. So you can adjust the frequency on here. So that's kind of that's kind of sketchy, because if you adjust the frequency and you have it designed for a certain size inductor, you could get shoot through, and that could be a little sketchy. So you can adjust all the faults, how it handles faults. Man, this thing is amazing. I'm definitely going to start using this when it makes sense, because this is a pretty expensive part. You can turn the power good. Oh, when it turns on and off. What the delays are, status, temperature. Yeah, so what do you think? Do we rely just on using I squared C? I mean, I think it makes sense still have a way for it to be hard coded. Because for the question, I was need to design a variable voltage. Control use net mega. GH maybe diagnostic. Yes, that's what I'm thinking. Brandon, with the GHGL, I think it's just for diagnostic. So maybe we'll just put it on a test pin. How do you switch the frequency? Like I said, you can switch it in I squared C, or you can also switch it on the RT sync pin, which is right here. it lets you synchronize multiple bucks together or offset, but it also lets you change the frequency. If variable voltage is chosen, yes, there is GN, but as long as you're accounting for the worst case voltage, which would be probably the lowest, which would be a harder, there'd be more current going through the inductor, I think it would be fine. But yes, certainly if this, like I said with the frequency, if you have this configured with like a 1 mic inductor for like a megahertz and you drop it to like 100 kilohertz in I2C, you're obviously going to blow something up. Add I2C and add some switches to have both options. 5-volt hardwired. Yeah, I'm thinking now probably hardwiring it, and then let it be adjustable with I2C. Switches, I don't think that would even be needed, because if you just don't want to use the I2C and just want it to be hardwired, you just wouldn't use I2C. I don't think you actually need it to VSET resistor must be present, pin should not be floating. Yeah, so then let's just assume that we'll do that for 5 volts, and then if you want to adjust it, you can just do I2C. Okay, so I think that makes sense. And like I was saying, I'm going to have the data sheet and then the simulation over on my other screen, so that's what I'm going to be referencing this whole time. And also, just out of curiosity, with like this board and then some of the other evaluation boards, what White Rabbit had said here. So I was mentioning one of the next evaluation board projects could be something with the new Pi Pico, and White Rabbit suggested we could have like an onboard USB and battery charger, lithium ion battery charger on it. So you could run it off of like a 1S cell and then just recharge it with a Type C. For stuff like that and this, are these things that you would actually want to buy? I mean, I'll do like some sort of poll or pre-order thing, but just kind of curious how many people are actually interested in getting these. And obviously everything's open source. I mean, if you set a resistor in a trim pot, isn't it pretty easy? Yeah. Like I said, it doesn't really affect me. Whatever you guys think. The reason I think they were saying not to use the pot is whoever had said someone, sorry, said that it only gets sampled at the startup. So if that's the case, you can't really adjust it on the fly, which is a bit of a pain. So to be able to adjust the voltage with the pot, you'd have to turn it on, check the output voltage, adjust it, turn it off, turn it back on, and keep repeating that. So that's why I think doing the 5 volts with a resistor and then being able to adjust it on the fly with I2C makes sense. But yeah, I mean, it doesn't matter either way. Oh yeah, pricing. Yeah, I mean, it's certainly, I mean, I guess to be fair, $3 for, even if this didn't have the I2C stuff, that for a 15 to 40 amp buck, I mean, that's a pretty good deal as is. So it's almost like you're getting all those other features for free. But we can just set the voltage with a resistor for now, and obviously if people think that we should change that, not a big deal to change. So let me see what the resistor values would be. $8.87K, outstanding. And I guess what I'll do for this, I use unique parts for everything. So like even a resistor would have a unique manufacturer, but for the sake of the live stream being semi-fast, I'll just default it to use KiCad's internal parts. Now the RT sync, like I said, that's to set the frequency. And one pretty cool thing, this isn't unique to this buck by any means, but let me see. So it allows you to set the frequency, or you can use a clock signal for synchronization between different. And it also, I remembered seeing, so standalone master, slave mode in phase, and slave mode 180 degrees out of phase. So that is really cool for testing like EMC and emissions, because if you have multiple bucks at the exact same frequency, it's going to be in phase and out of phase randomly just by drift, because they're obviously not going to all be identical. So your emissions are going to be all over the place. It's not that they can't still pass, but it's not consistent. So if you have a clock for all of these and it ties them together, you can either have them all switching at the same time or offset from each other. Obviously, if they're all together, you're going to get more emissions at that frequency because there's more added, but it'll all be focused at that specific frequency, where if they're out of phase, you're going to get more smearing. But obviously for this, we don't really care about it. It's just, it's cool when they give you that option. So I'm thinking, oh, that's funny. So I was thinking of doing the frequency at 1 megahertz, and the resistor size for 1 megahertz is 8.87K. I am going to go out on a limb and say that they planned that. That's funny. Okay. Address, that's obviously to adjust the address of the I2C bus if you have multiple. Let me see what actually we do to adjust it. Normally it's just high or, oh, well, that's pretty cool. They actually let you do a crap ton. Normally it's like floating high or low. Here you do different resistor values. I wish more ICs would do that. So let's do 8.87K. So then that's the address. I guess that's something we should probably have a jumper for in case you want to use a different value. Or I guess, truth be told, since I didn't get a huge message response that people would be interested in buying this, I guess the true flexibility there would be whoever assembles them. So maybe we'll just keep it 8.87 for now, and we can always adjust it. Hate how much room that takes up, but I guess that's fine. Okay, now VDD, that's, I believe it has a 5-volt or some sort of LDO that you usually just have to use a decoupling cap. Linear regulator, yeah. So let's see, I'm pretty sure 1 mic. Got it. And to clarify that internally, so if we go back to the block diagram, so power comes in on the VN pin and it gets dropped on the linear regulator, and we decouple the VDD pin out here to help with noise, and then that uses that 5-volt supply, I think, internally for its control logic. It's super common on not so much bucks. I mean, I guess sometimes it is, but it's pretty common on higher voltage ICs that need to be able to do something internally logic wise, and they can't go off of the internal. Now the PVCC is, I believe, the same thing. Oh, that's used for the gate drive, so they want a 4.7 on that. And as for the size and components, I'm not really sure. I don't know if you guys care about keeping this like super or again, I guess if this is going to be something more of just a teaching thing and not actually something that people would buy, I guess it makes it a moot point. But I don't know if this necessarily needs to be kept as small as possible, because I don't think that this would be something you would ever like try to incorporate in a final project or final yeah, project, because this obviously wouldn't be in something you would sell. Oops. And yeah, I am kind of anal with making sure this kind of takes up the least amount of space. Just like these two, it would annoy me if they're not at the same height. And then the problem with that is now it kind of annoys me that these aren't centered on here, but this one is. So we might have to remedy that later, but for now, I guess it's fine. Supply voltage for internal gate drive. Yep. What's funny is in the datasheet video, I literally mentioned that. And we won't have pull-ups on this board since this will be a slave. You never put pull-ups on the slave side because you only need one pair of pull-ups on the I2C lines. And just a refresher, if you don't know I2C, to be able to use I2C with different voltage or logic levels, say if you have like a 3v3 device with a 5-volt logic device, it's active low, so you have to pull it up, and if you don't have pull-ups, it typically won't work. Sometimes it still does. So you have to have usually like a 4.7K pull-up on every I2C bus. But like I said, it should only be a single pull-up, and it'll be on the master side, so we do not have to worry about it here. Okay, so now we have our I2C out there. Does it affect to have pull up on the master and slave? I mean, no, it doesn't matter, but just keep in mind you're forming parallel resistors. So if one of the I2C buses doesn't have the drive strength to pull down like 2K or something, every time you add a 4.7K, you're reducing the resistance. So if you do it enough times, yeah, it's not going to be able to pull it down. So typically, not even for long traces. No. I mean, I've never heard of it. I could be wrong and there's a use case, but I2C isn't used for anything outside of like sensor boards. I think it's only rated for a few meters. So anything super long, you're not going to be using it anyway. Okay, so VN, PVN. I guess we can just tighten these up for now. Adafruit puts weak pull-ups on their I2C boards, 10K. Yeah, that doesn't surprise me because a lot of people probably forget. And 10K would be a weak enough pull up to where if you did put a 4.7K, it's not going to screw things up. So do you want to have pull ups on here? I kind of would like to not, because then we have to take it from our VCC or VDD pins down here, since we won't have 5-volt logic, and I don't want to have to take it from the output side. I mean, I don't think it makes sense in this case since we don't have the supply here, but if you do, let me know. Now, P good, those are almost always open drains, so we do have to have a pull-up, but let me check. Yes, it is. So here, going to the block diagram, P good, and like in my video, you could find that on the block diagram, or you could find it here. It'll say it in the same spot. And then I guess, oh, this is what I was going to ask earlier. What do you guys think about indicators? Should this have LEDs for P good? Should have like an indicator for enable and an LED for input if it's good? The output if there's an LED there. What do you think? I mean, I normally don't, but since this is for a like a test board or evaluation board, it might make sense. Oh, we're gonna have to pull that up to logic. Let me see what they do in the... Okay, so in the simulation, they pull up P good to the VDD pin. So presumably that's the safer bet than the VCC. So I guess to be fair, then we could pull up the I2C lines, but I'm not a huge fan of that. For a module for sale, you could have separate VCC for the pull-ups, and then people could not connect it if they don't want pull-ups. Ah, got it. That makes sense. Or now that what do you guys think now that seeing the pull-ups to VDD? So what if we... Here, let me... So... and just FYI, guys, when you say, like Brandon said, yeah, I'm into it, I know you were referring to as... however you pronounce Asborn's name. If you're responding to something I said, don't just say that. Say what you're referring to. I have like a 20-second delay, so I don't really know what you're referring to when you say that. So let's do this. So now we have our VDD. Can someone check in the data sheet what is VDD, like voltage-wise? I'm assuming it's 5 volts, because if it is, then we have to be aware, if you try to use this with a 3v3 logic board and we do enable the pull-ups, it's obviously going to screw everything up. So let's do some jumpers then. So we can have, I guess, just a single jumper like this, and we can have VDD here. And now we can have our... I hate this. It's going to take me so long with the new KiCad, how you have to highlight it and then, or you have to click it and then do copy. You can't just do like the lazy selection, which, I mean, I guess it makes sense why they do that, but internal 5 volt, perfect. So it is 5 volts. So then, oh, come on. So we're just going to have to then make a mention that it's 5 volts, and you're gonna mess stuff up if you use this with 3v3 logic. Okay, so there's... Oh, it would help if you have resistors. I'm gonna be curious if someone comments that before they before I see the delay on it that I forgot the resistors. Does it matter if it's before or after the jumper? No. It's also going to take me a minute to figure out where everything is. Oh, and by the way, this is the latest nightly. I downloaded it tonight. Downloaded it earlier today for tonight. Put it to an external pin for vref. How about we do this? Yeah, I forgot whoever said and I had an idea, but then I completely forgot about that idea. What if we do this? And I know it's kind of a pain multi-jumpers, but I do think it makes sense. So what if we do this? And see, like, that's off center because it's an even spacing, so that will not fly with me. So we have to even it out. And then, like, another thing that I can't have is now these are at different lengths, so we have to copy the length and then make that. Okay, so how about that? So now we have the ability to enable the pull-ups at all with these two, and then we also have the ability to adjust which is pulled up. Connect VDD to pin 2. Why would I do... Oh, you deleted it. Okay, I was going to say, I think it's good. Have you noticed any bug fixes? Not yet, but I also haven't really done much. Oh, one bug that's still here that drives me nuts. So for projects, the way I do my project structure is... Oh, okay, so here's a bug fix that they did. So I use the... Kai project mod for my library path, and since I have my project in a separate folder than my libraries, I have to go up a couple levels, and I do that with the dot dots. And before this version, it wouldn't actually follow it when you clicked here, but now it does. So that's pretty nice. Oh boy. Okay. So I squared C pull-ups. Now let's make a note. Onboard 5 volts. And external 3v3, because if it's not external 3v3, it doesn't really make sense. Why not just put level shifters on it? Oh boy, that's a little excessive, I think, for a pull-up. Maybe remove both JP on the resistors altogether. Maybe remove both jumpers on the resistors, so both of those gone, and keep the 3-pin selector. Oh, yes, I like that, because then all you would do, if you don't want to use the pull-ups, you would select external and you just wouldn't put anything on it. I like that. Good thinking. Okay, so now I think that makes sense. So if you don't want to use pull-ups, you would jump 2 to 3 and then just not apply anything here. If you want to jump it, if you want to use onboard pull-ups with 5 volts, you jump 1 to 2. And if you want to use onboard pull-ups to 3v3, you do 2 to 3 and then apply 3v3 on that. That I think makes sense. Sweet. Okay. So I think that works. Let's put that over there. Make sure I didn't miss anything. Oh, Bradley, you would buy one. Fantastic. Will you go over the certification process? Hang on. And it's just water. I know I've been asked that a few times. So I'm going to be using, if I do end up selling this, I'm going to be using the SparkFun and Adafruit method to where, since this is a sub-assembly, to where you can't use this in and of itself, it has to go into something. You do not have to do any certification for it. I have been thinking, because I've mentioned it a few times, I want to start doing a series on EMC testing and some different like in-house tests that we do and that are useful. And I was thinking this could be a good project for that, but no, there's zero chance that I would get this certified. I highly doubt enough of you guys would buy this to make back the money. Okay, so now, what do we do with P good? Do we pull it up on board with VDD? The issue with that, again, is if it's going to 3v3 logic. What if we do this? What if we make this global? So we do, like, pull up voltage. Please do an EMC. Thank you for clarifying. I would love that series. Awesome. Yeah. Trust me, I've been more excited about that series than, like, anything I've done on this channel. It's just getting everything sorted with that has been kind of a pain, and I definitely will be doing that. I did not know I had odd traces on there. But I will get to it. It just might not be for a while. So what do you guys think then about this for the pull-up voltage? Because there's no way anybody would ever use this with a different voltage on P good and I squared C. So that gives you the same flexibility here. You can apply no pull-up if you want to do it off-board, or you can do the onboard 5 volts. I think that makes a lot of sense. Okay, so there's our P good. And then we have over 40 people. That's awesome. I think that's close to the record. I think we've had 40 on here at one time. So now you can access P good. Now the enable pin. So will you make the USB hubs IRL? Man, I've wanted to, but the problem is, like, half the parts are out of stock. So I would say yes, but probably not for a while. I do plan on it because I think that one would be cool to sell, just because there's nothing out. There's nothing out there like that. Well, without jumpers now, S squared C are connected with 20K. If SCL is pulled low and you have a weak 10K elsewhere. True. Crap. So what he's saying is, let's say what Rotor is saying. So let's say you're using the option for offboard. So it's essentially like this. And let's say you use a pull up over here. No, they're still on the same net, because you still have to have these pull ups somewhere. Yeah, because that's how it would be used everywhere else. Because the resistance is here. Oh, no. Yes, I see exactly what you're saying. Yeah, I see exactly what he's saying. So basically, now if we have 4.7K, so now this, let's say, is off the board, and we're pulling this up to, obviously, it would be, okay, it's not exactly what I wanted. So now we're pulling this up to 3v3. Now we do form a divider here. So yes, I think we do have to have those jumpers. Yeah, rotor, but they have to be pulled up, or else you wouldn't be able to use this. P good, be good. How much power can P good handle? I've seen loads of chips that can't even drive an LED. Not a clue. Good question. If so, then you would just need to use a buffer, which it doesn't say. So remember how I said data sheets can suck? Yeah. Here's one of those times. So it's an open drain from a FET, so I don't know how much this can sink. The fact that it doesn't say usually would mean, to be safe, you would just want to use it for logic and use a buffer of another FET or something. Yeah, and they don't say what current you use here. I mean, I think that's fine because they're not actually going to be connected to each other with 10K. They're connected 20K. I don't know. Let's keep it for now and we'll see. Now, something that's super important to look at whenever there's an enable pin, and this bit me on a job for work like 3 weeks ago, and it gets me all the time because I just despise ICs that do this, and I don't know if this does it or not, but it certainly is something you have to look at. So absolute max ratings, so PVN, so yes, this is one that does it. So this is absolutely obnoxious. So if you look at absolute maximum, all other pins are VDD plus 0.3. VDD is 5 volts. So that means on all other pins, you can't have more than 5 volts applied. So what does that mean? Our enable pin, if we tie it to here, we destroy the IC because you can't have this at anything above 5 volts, which is quite obnoxious. If you use VDD on your own board, it is fine, but if you leave the jumper floating and have the pull... Yes, no, that's what I had drawn out. I definitely agree that it is, but the fact that we're talking a 20K resistance between the two, I think it's okay, but we can come back to that for sure. So now, how to do this? There's a few things. The board that I was talking about, what I typically will use is... so this is on our internal library, which I'm not really going to use because these are all old version of parts, and I don't want to have to import them. KiCad 5. But essentially what you can do is you can have a Zener and then whichever value resistor you need with it. I don't know, since this is just a generic example. So now So now if we apply, and obviously this is not how I'm going to keep it, but if you do something like this, and this is obviously to keep it on all the time. So you have your main power coming in, it gets dropped across the Zener, whatever voltage or the current's limited by the resistor, and then it clamps it at 5 volts. So that's a cheap little way to do it for any input voltage. You can also obviously do a voltage divider with 2 resistors. VDD should not be affected by enable though. I don't think that's not what I'm saying. What I'm saying is VDD should not be affected by enable. No, I actually don't know what you're talking about. All I'm saying is if you're applying 20 volts here and you have your input directly attached to enable, you blow the IC because enable can't handle 20 volts. So if you want to keep it always on, which is kind of the purpose of a buck, or at least in this case, this is something you can do to alleviate that. What the simulator does is they have just a voltage divider here, which if you know what the input voltage is, that works fine. If you don't, like for this, where it's 5 volts up to, or what did I say? Like 10, 12 volts up to 20 volts, you have to be careful with how you pick this. And since that's going from 10 to 20, you're going to have the voltage that goes here. So that's kind of sketchy. So are you guys fine with doing this and having it always be on? I'm saying that the LDO is not controlled by enable, so VIN should cause VDD to supply. So you could just connect. Oh, is that true? So that's one of those things in a data sheet where you have to have some faith. So to clarify, what they're saying is, and what I did here will work. Like I said, I've used it a bunch, but what they are saying is, so what you have to be really careful, and I've done this before by accident. So let's say we have all of our switching nodes, it's doing its thing, and we have 5 volts out here. So our output voltage is 5 volts. It might be tempting to take this 5 volts and tie it straight to our enable pin. The issue is when you apply power to this board, the enable pin doesn't have 5 volts because it hasn't produced an output voltage yet, so it will never turn on. So you have to make sure you have that 5 volts available before you turn on the entire IC. So what they are saying is tie enable to our VDD like this, and as long as it produces the 5 volts on VDD without having to be enabled, we should be good to go. That scares me for 2 reasons. One, that's not how they do it here. And since this is wired up to be on at all times, they presumably would have done that, especially since they're already using VDD elsewhere. I would think they would just tie it to it because that's easy. And the other reason is, unless you guys saw anywhere else, it doesn't say anything explicit about it. But I guess let's see. But yeah, I mean, it should. It doesn't go through the control logic. It's separated from anything with the enable pin. I mean, it still is a little bit sketchy, but I think that's fine. I don't know. What do you guys think? How scary is that? If this was a board I was doing for work and I just wanted to keep it always on, I would do the Zener just because I know that's going to work. But this does give us the advantage of, one, for the eval board being a few less parts, and then perhaps it makes it a little bit easier. Put it on an enable pin and then a pull up. So I guess what we can do, so I guess the other question, do you guys want it to always be on? Or do you want to have a pin to be able to turn on and off the output? The only time I can think of where turning off the output would be useful is if you're messing with configurations in I2C, but if you're messing with configurations, wouldn't you just disable it from I2C altogether? But maybe it does make sense if you're troubleshooting. I think it's unsketchy. Never heard that. Well, VDD is supplying control logic, so why wouldn't VDD serve enable? No, that makes sense. Yeah, I can buy that. Always on is okay. So then let's do this. Let me know what you guys think. What if we put a jumper and ignore the always closed thing we would presumably use. Why would you want to turn it off? That's what I was saying. The only thing I was thinking is, let's say you're trying to configure I2C and you have this connected on the output and you just don't want to have an output voltage for whatever reason. You can just force disable this. So what I am thinking, yes, let's go bold. So what if we do this? We pull up enable to VDD, and then we do our jumper. Input current, IV in, TD non-switching, V out, VSET 3.5 to 6. Input current, huh. Go figure. So what do you guys think about this? So it's by default always going to be pulled up to VDD, so it'll be on. And then wait, you're saying it needs 6 milliamps on like that? No, there's no way. These are just inputs. They wouldn't source that much at all. I'm sure I'm probably just misunderstanding what you said. So, oh, and that's uneven. We can't have that. So what do you think? So now we can put the jumper on and let that go, and then whatever on the other side. I think that works. The only nuisance is now it makes this not very clean because it runs over that. Let's do this. And this is something I've mentioned a few times that I'll do. Is I'll go back in here and change where this stuff is. So if we do and move all these pins down some and then put our input here, our enable pin, that clears it from our PVN side. And now we have to update, which is new on nightlies. And now let's move all of this. So let's move this out of the way, move this out of the way, that back down, and like that. I built revision 1, 100% working. Yeah, that's always the dream. I would put a enable pull down resistance. Why won't you add a MOSFET in parallel to the jumper? Because I think if you're using this in an actual board where you're going to control it, you would just use I2C, I would assume. Plus, we would just tie it to a connector and let it toggle from the outside board if we wanted to give that much control. We wouldn't need a MOSFET on our end. So now Okay, so now we have our pull up by default. We can turn this down. And yeah, why don't you have a pin and the pin gets pulled high? I'm assuming you're just saying flip-flopping. I think either or works fine. I don't think there's a big difference either way. How's it going, John? Glad you made it. Okay, so now have our voltage, we have our frequency, and let's do and look at our address. Well, I use a PR sensor to control an ATX. True. Well, if that's something you guys want, let me know. We can add something on the enable. We can add this. Yeah, I mean, we can certainly do that. I see nothing wrong with that. So now we can break out the enable pin when we break out the other stuff. So if you want to control it with something else, by all means. Okay, so that's all sorted. Oh, and something that Bradley had mentioned the other day. So he was asking about analog and power grounds. So, and I actually don't know how this handles it. Um, oh, that's very helpful. We have no idea where A ground actually connects to in the block diagram. That's helpful of them. Oh, here we go. Okay, yeah. So Bradley, if you're still watching, so it's exactly what I was telling you. So basically, they are using a separate analog ground for the voltage sense because they want that to be a cleaner ground or a reference for sensing the voltage on the output side. And my assumption is that's the only thing that they use that for. And they are using a separate analog ground pour. So essentially, like 98% of the time, trying to have a separate analog ground and a digital ground is going to be worse than if you just tie them both together. You have to be really, really, really careful and keep everything separate, but make sure nothing ever jumps the gap except where you want it. So it's kind of like when you're deciding, like, should I use a 2-layer board or should I use a 4-layer board? When in doubt, use a 4-layer board because it's going to turn out better 98% of the time. Same with this. When in doubt, just tie them together and then do your best on the layout to keep the analog ground pins separate from the switching node when they go to your vSense. But as long as you handle the layout correctly on that, it's going to be totally fine because in every other buck that you'll do, they will just have a single ground. And on your feedback resistor, as long as you route that correctly, you're not going to have an issue. But of course, if you're using a board where you already have an analog ground plane and you're able to sort that, it's useful. But when in doubt, tie them together. C does not equal 0x C. Yeah, I don't do the whole programming game too much anymore. So that's what they said on there. So that's what I went with. Okay. So what did anyone have any opinions? Well, we can worry about the LEDs later. Okay, so I don't really want to, so something I'm going to do, and honestly, it's kind of sad that it took me till just now to think about this. So, yes, I've heard, you're welcome, Bradley. Yes, I've heard there's no issue combining analog digital unless you trace a clock. Yes. And again, that's the gist of what I'm saying is if you do the layout correctly, it doesn't matter. If you keep your analog returns away from digital, it doesn't matter which ground return they're on because they're not going to be interfering. It's just when you separate them, it makes other things that much more likely to come into play. So this app note 1197 is pretty much the main doc that I use for choosing inductors for bucks and figuring out the current ratings of them. What I'm gonna do, because there's a bunch of equations, and like I said, it's kind of sad that I never thought of this. I'm gonna make like a Python program. As I just said, I don't do programming. Well, I try not to. I'm gonna make a Python program to where it'll spit out all this, so I don't have to calculate them by hand. And I don't want to do that on the live stream, go through all these. So what I'm gonna do for the sake of time is I am going to just trust the values that they have on here for values, and just use the 1 microhenry inductor and just go with it, and we can do the calculation and confirm later. But what is kind of funny, and it doesn't lend me very much confidence, is yeah, definitely not quite as good as WeBench from what I'm seeing. So this is set at 10 amps. So your inductor current, your peak and RMS, they're going to be higher than the 10 amps. So your saturation current, you would want to be pretty high. And this is rated for 4 amps and a saturation of 7 amps. So this inductor likely wouldn't work. It would be saturated. But I guess don't tell them that. They tried. Oh, another fun thing. So I'm not using this full screen on my other monitor so I can have the chat open. It doesn't let me scroll over. Oh, never mind. Had to use my center mouse. Okay, so all that said, we'll just trust their inductor value for now, and we can adjust it later. And on the footprint, these are all tied together on the pads themselves, which makes it kind of nice. Okay, so we have here, and then I guess we can do, so if you weren't here towards the beginning, G, H, and GL from the best we can gather, they're for oh yeah, we're gonna add test points. They are to monitor the gate drives on the high side and the low side MOSFET. They don't say what they are, or they say one of them, that's what it is. So we're just gonna run with that, which likely that's not something you would troubleshoot. I mean, I've troubleshooted or troubleshooted. I don't know. I've troubleshotted a lot of bucks before, and I can't say I've ever monitored or wanted to monitor that, so I guess it's nice they have it. What's the saturation current and the normal current of the inductor? Yeah, so I forget the exact specific example of when the saturation current. So here, let me pull up that inductor again. Oh boy, that is not it. Troubleshot. So it is troubleshot. So looking at this, so when your current is saturated, that's when it just has a shoot through, so it no longer has, it's not a when it hits that, it's instant. There's usually a need to it, but above this, it stops acting like an inductor. But then you're asking, oh, what is the current rating? How is that lower than the saturation current? And I actually looked into this a little while ago. I forget the exact reasoning, but logically, yeah, it doesn't make a ton of sense. So, what I always do, and actually right before the live stream, I started looking up inductors that we could use. And oh, that did not work. Oh, yeah, it did. So what I always do is, when we do the calculations, we'll find out what our peak inductor current is, and you want to make sure the saturation current is above that. So what I will always do is make sure the standard current rating is above that also. So that makes it safe on both counts. But yes, how the current rating can be below the saturation, I would never use it like that. I would always have both of them above it because logically that's what you need. Basically not a short but a resistor. Yeah, but I mean he's not wrong, because if you're using it as an inductor and it stops being inductive, yeah, it might be a resistor, but it's still a short in the sense of no inductance. Rated equals typical usable current. Yeah, Mickey, but what the point being with that is, if the typical usable current is when you can use an inductor until the saturation point, but what about above the max current but below the saturation? You're not saturating the inductor. That's what he was saying. And I know you know that. That's just the part that I don't, that's kind of funny to me. But Kate, point being, it doesn't matter. I would never use it in that case. 14 ceramic caps? For real? Well, I think we might have found a glitch in the matrix here. I don't think we're going to be using 14 ceramics on, what is the PV sin? I don't even know. PV sin. Okay, it's not even in the block diagram. Lovely. PV sin isn't on the schematic. So yeah, I definitely think we found an issue here. What is PV sin? Does anyone have any idea? Because on our typical application, we don't even have that. Did I use the wrong part? SiC 453. No. Vsen positive. Yes, that's it. Yes, positive voltage sense minus voltage sense. That's funny. So I just don't understand why this would be calling for 14 ceramics. And what are they rated at anyway? Because the problem is, like I said, with us trusting this, we would have to then go back and do all the, oh, not recommended for new designs. That's nice. 6.3 volt. So that's just because this thing is so derated that it's not even going to work. Or it's probably at such a low effective capacitance. It's probably at like less than 1 mic. VSEN plus common mode range negative point or VSEN -2. So it maxes out at 12 volts. So I'm assuming the simulation is just taking into account the effective capacitance, but how do we change this? So they don't have any others with a higher voltage range. Why? Why not? $10 volts, 16, 25 volts. So let's see what happens when we put this here. It's still gonna want the 14 there, yes, because I didn't change that. Oh, really? Outstanding, Vishay. Okay, we did go back, so does it let me run? No, it doesn't. Okay. And then I also have a good app note that I use for output caps. I'll pull that up. But yeah, that'll be something I'll work on here, is getting like a Python program that'll calculate using the TI app notes that I use. It'll calculate input, output caps, inductor, all that. And I've mentioned this app note before, but only for the input caps. So SiC45x. And that is for output. Oh, wait, no, input. And then this is the part that's super cool. It helps with calculating the inductor size or the bulk capacitance size based on using like a pi filter or something. And here's our output caps. And then they do like a full example-ish. So, and this doesn't actually do anything. And it didn't even update. Oh, it didn't make my change if it take it into effect. But anyway, I don't want to spend a ton of time messing with that, since obviously we're going to have to do these calculations, since that simulator's obviously not something that can be trusted. So what we'll do then is just have, I don't know. What I'm curious about is if there is something with that sense configuration that it requires more ceramics than normal, because normally on, so with a buck, since we have an LC right here, the output is filtered as is. Where the input side you don't, so you have to filter the input side a lot more than the output. But that is, I guess we can just do like 5 as a placeholder. One issue with normal voltage sense lines out here when you're using a voltage divider with a resistor is what? Well, speaking of a bug, normally you have to have a certain amount of ripple for the sense on the resistor to be able to read it. So if you have too much ceramic capacitance out here, it's going to cause there to be issues calculating the output voltage, and sometimes you have to do like a ripple injection circuit where you have to force there to be ripple on the output. But for this, since it's measuring it straight across, it probably doesn't matter, and maybe that's where they're going on about. Architecture delivers ultrafast, yeah, with minimum output capacitance. That's funny. Wait, this LC is part of a buck circuit? Yeah, buck has the cap on the output side. So as a rule of thumb, bucks cause noise and EMI and EMC side issues on the input side, where boosts cause it on the output side, because whenever you have the inductor with caps, it's going to smooth it out. So when you're doing a layout, and we'll obviously be messing with this when we do the layout later, but this is your noisiest part of the entire circuit. This switch node is the most critical part of any buck converter. And if you go to here, if it's not the first or the second thing, then the PCB layout suggestions on this are complete trash, because that's absolutely the most important side. Or it'll talk about the switching node and the input caps as the most important. So VN and P ground, yes. So that's correct. Different values / packages. Oh boy. We might have a EMC video proving them wrong here. That's funny. So that's super old school thinking, having different value capacitors at different sizes, because it forms a anti-resonance peak. And that's something I'm super, super excited about doing the testing on the EMC side, because that's wrong. The last EMC consultation that we did, that was one of the suggestions in it. Under 500 megahertz, it made a pretty substantial difference. Above 500 megahertz, it didn't do much, which makes sense, because above 500, the interplanar capacitance makes a bigger effect. But it is kind of funny that people still do that. So they actually, yeah, so I'm not a big fan of this if they're not mentioning the switching node being crucial. Okay, so differential pair. Oh, because it goes into the op amp. Well, that's pretty interesting. I didn't know that. Very cool. But yeah, here they say keep it away from the switching node. So I don't like the order that they said, but essentially this is the noisiest part right here, because it's switching on and off. And you want to keep this trace as far away from this as possible, because if it couples to this, you're going to have a crap ton of noise, which you do not want. It's going to cause a ton of issues with your output regulation, or your regulation of pretty much the whole buck. Step 3 is switching. Okay, I must have just missed that. Well, that's good then. But yes, I do take back at the first step should be the input side, but the most important thing to keep away from is the switching node. That's what I meant. Oh, that looks bad. I guess let's just do this, and then we'll have to redo all that. I just love the audio version of EMC. Yeah. It is funny still when you get a buck, and so bucks in light load, and this actually is with a project we're doing right now. On light load, they'll drop the switching frequency a lot to make it more efficient. And if it doesn't have a ultrasonic mode, which this one I believe I remember seeing it does, it'll often make an audible noise, which is kind of annoying. But once you put any sort of load on it, it should go away. And yeah, it's normally the ceramic caps that'll make the most audible noise. Okay, so V out. Then why won't you add another cap on the V sense plus line? I mean, these are connected to the same node, so they essentially are. I mean, yes, I could certainly be more explicit and add some there, but they're going to be the same thing. And like I said, these are all just placeholders. We're going to have to calculate that better, because like I said, that simulation side is not all that great. So now for the boot pin, we need to have our bootstrap cap, and they require, at least in the simulation, a resistor in between, which presumably is just to limit the current. And they want this to be a 0.1 mic or 100 nanofarad. And they're saying 2.2 ohms. Probably helps with noise also. I mean, add caps closer to the input filter. Oh, for sure. Yeah, I mean, I don't disagree, especially if you route these as a differential pair. Then you certainly should. But schematically, they're equivalent. Okay, our bootstrap here, switching node. There's our V out. Do we add a fuse? Obviously, trying to keep this somewhat cheap. We're not going to add any more elaborate overvoltage or overcurrent unless you want like an E-fuse, which, as I have found out way too unfortunately, I should say, that pretty much all E-fuses, or a good portion of the E-fuses, are out of stock because they're used a lot in automotive. So there's not a lot of options there, which is kind of an issue for a couple projects that we're doing right now. So maybe we just put like, what's this rated for? 10 amps or 15 amps? I think 15. So we can just do a 15 amp fuse there. The chip has overcurrent built in. Sure, yeah, they all do. But yeah, we can probably trust that, because with I2C you can set that. But if this is something that's actually going to be used, like say if this was needing to pass UL, you wouldn't be able to rely on that because it has to be single fault tolerant. So if that didn't activate, what else would protect it? But yeah, I think that's fine for this. Good thinking. Okay, so that's everything there. Now we need, isn't a fuse for input pins? No. Fuses are more I mean, it depends the way you're using it, but the rule of thumb that I use is, say if this was incorporated on a board with a microcontroller and other stuff, anything that leaves the board that is powered gets a fuse on it, and it gets the minimum value fuse you can manage. So if you short something off the board accidentally, say it's in a metal chassis and it gets shut and the wire's cut and it shorts, it's going to pop the fuse on here. Where on the input side, as long as all of your outputs are fused, that input shouldn't ever be used. But I'm actually potentially going to work on a video sometime about how input fuses can be useful, especially if you have like Zeners for transients, because we had this board that draws a lot of current. It's like a 50 amp board, and there's a 50 amp input fuse, like it's massive, and it has a couple Zeners to help with transients, and I don't know what in the world happened, but that 50 amp input fuse blew. This was like a month or two ago, and it failed perfectly, no burns or anything, and it's like, that's just terrifying to me. What would have happened if that fuse wasn't there? And it's like, how massive of a transient that must have been. Ask an electrician, he would tell you it's only used to protect the cables. Oh, totally. And that's, I was gonna mention that. So on the when I do the output fuses, I said the minimum value possible, but that always has to be no bigger than whoever you're using, IEC or whatever rated for the wires, because your big issue is, in my example, if you shut the chassis on the two wires and they short and you don't have a fuse and it doesn't clamp the voltage or it doesn't clamp the current, it's going to either melt the wires or your traces on the board. If it melts the traces on the board, everything on an FR4 board is pretty fire retardant, so you're probably fine. But if those wires melt, they should be flame retardant, but I've seen wires catch on fire a lot more than I have seen boards. So, yes, ultimately you want to protect the wires and the board. Hello, PCB Design. That's a fantastic name. Okay, so now on the V inside. So they are saying in the simulation we only need, and what's also funny is in the data sheet how I was saying the thing about using different size capacitors, yet on their simulation they don't. They only have their bulk and then a single 0.1 mic. By the way, DuPont cable makes fine fuses. Yeah, everything is a fuse if you try hard enough. Okay, so now this is the part I'm kind of unsure about what we're going to do. Since most of the stuff that I do for work is kind of industrially and BOM cost isn't typically a huge concern, I always kind of go overboard on input filtering, but if this is something that people might want to buy, one of the easiest ways to add cost to a buck is filtering, because ceramic caps are pretty expensive at large size. So essentially, so if we have this buck, let's ignore the input. Man. So if we ignore the input side, if you do a good layout here, as long as you keep the switching node to the inductor short, anything out here is going to be filtered, and there shouldn't be much radiated noise from this side. And this is only with a buck because, like I said, the buck is on the output side. So if you do a good layout on the output side, you should be fine with EMI and EMC issues. The input side, since this is where the true switching noise is coming from, so if we look at our block diagram, so we have our switching node, right here, which is being switched from the FETs. So that is a very noisy node, which is then filtered by the inductor. So that noise radiates, but as long as you keep that pretty short, you're usually fine. Then where the current is coming in from on the, where's the P? Oh, PVN, yeah. So on the power input side, that switching node is being drawn from the PVN at the exact same frequency, obviously a different current because the voltage is different. So that noisiness on the switching node is also on the input side. But since it's a buck, you don't have this inductor here. So all of that switching noise, and let's say we wanted to be real fancy and we wanted to have a ton of ceramics here and filter this really well with ceramics. To a certain extent, that helps. But as a big overgeneralization, and this is a big one, but if you don't have some sort of filtering on the input of a buck, it's not going to pass EMC. So, and that's because no matter all the ceramics here, you don't have any inductive component. So that noise is going to radiate. And then if you have your input right here, it's going to radiate on your cables. And it's going to radiate all the way back to your source, which your cables are 6 feet long, 3 feet long, and that forms a perfect antenna. So you have to have something on here that filters. And the kind of the rule of thumb and what my experience has been with doing EMI certifications is ferrite beads work. They work fine. But the best thing to filter a buck is a pi filter. So a pi filter is what we have on the USB hub. So we have, and they call it a pi because you have your input caps, your inductor, and then your caps on the other side. So it forms kind of like a pi. And this gives us that inductive element here. So this side is noisy. As long as you keep your loop to the buck short, that won't radiate that much. And the key is this side is quiet because it's filtered by the inductor, and then your cables are out here. And because now this is not a switching node anymore, there's no radiated noise. And we also have a common mode choke. So if there's any differential to common mode conversion elsewhere on the board, the common mode choke will help with that. So one of the EMC videos that I'm going to be working on is comparing a pi filter to a simple ferrite bead. And a ferrite bead acts like a lossy inductor. So if we pull up if we look up a of course you need cookies. Oh, really? Well, you obviously don't get used. That's the exact same one, isn't it? Yeah. Okay, well that, oh, it's still not showing it. Because I want to show where it has the graph where it shows the points better. Okay, well, anyway. Really, all of these? Okay, so here's a ferrite. Okay, so I don't want just the impedance graph. Okay, here we go. So the ZRX graph. So at a certain point, the ferrite bead will change from being inductive to being capacitive, and the resistive element, which is the R here, will be more effective. So it becomes like a lossy inductor. So if you're in the frequency point, I can't highlight, but if you're in the frequency point to where the resistive portion is high, it works really, really well. But if you get past that, it becomes capacitive. So it just passes the noise through. So ferrite beads, if you choose the values properly, they work really well, but the issue with them that you don't get with an inductor near as much is you don't have to worry about that point where they become more capacitive. So long story short, you use a ferrite if you want to save money, because with a ferrite you can just have it here and you don't have to have bulk capacitance on the other side more than what this needs by default. But if you do a pi filter, you do, which is why here we had to have almost 1,000 mics of bulk capacitance. If we didn't have this here and we just had a ferrite, we could have gotten away with probably a tenth of this and just done like maybe 100 mics or something. So what do you guys, that was a very long tangent, sorry if that was more than you wanted to hear. I don't know, what do you guys think? I mean, we can just throw on a simple ferrite, because the problem, if we do a pi filter, we're gonna have to do can we crack on a bit? Yeah, so I mean, do you want to just go with a ferrite and call it a day? What do you guys think? Because if not, we're gonna have to do a decent bit more calculations, and I'd kind of like to finish the schematic pretty well tonight. Nearly, it's way after midnight. Yeah, it's 6:42 p.m. where I am. Which is funny because everyone on Discord, when I do the polls, everyone wants to do it at this time, and it's kind of funny because it's like for people in Europe and all that, it's so late, and it's like I kind of think you guys would want it earlier. Ferrite for now, then you could show pi filter and follow up. Design it like you would for passing regulations. Well, that would depend on how much money they want to spend on the bomb cost, because if it needs to pass no matter what, I would certainly use a pi filter. Go the ferrite, yeah. So that seems to be the consensus. So here I can pull up a ferrite search. So our input, what output, we're gonna be 15 amps at normally 5 volts. So we're at 75 watts. Input, worst case, we're at 10. So what if we rate it for, I guess, 8-ish amps on the input side? I think we're okay. Something like that. Ooh. And okay, so that's another thing with ferrites, is when you get into higher current ratings, your selection goes down a ton. And that's when, again, it kind of forces you to use a inductor, a true inductor with a pi filter. But the prices are pretty insane. So power line, signal line, those are kind of irrelevant because they will filter them on their side. Like the manufacturer will lump them into categories differently. So I usually don't filter it there. Now impedance at frequency. So of course the impedance is the total resistance at different frequencies, including inductance and resistance. So of course you want it to be 6,000 at 37. You obviously want that to be the highest value you can at the frequency. But the issue here is, again, anything above that crossover frequency, it becomes capacitive. So you do kind of want to look at the charts and how to pick them. It's kind of a pain because you have to look at the charts. I trying to see. I normally will use Borns, and I've actually used this series in the past. Oh, what was the part number? 2029. Is that it? 0? No, 100Y. 100Y. So if we are trying to keep it below, say, the 10th harmonic at 1 megahertz, that puts us at 10-ish. So at this point, we're not going to have a huge part of the resistive component. It's going to be more of just a very ineffective inductor, but any of the higher frequencies on the harmonics, it will up to like 100 megahertz. So this is probably okay. Ideally, we would have the resistive side start a little bit sooner. But I think that's an okay start. Let me see. Hang on. I'm going to look up another ferrite that I used in the past. Can't find it. Okay, let's just do maybe a higher frequency or a higher current one. Murata and Borns I use quite a bit. Do they not even have a chart? Lovely. In one thing, just as you're kind of seeing me looking at these charts, this is one issue with a this is one issue with a ferrite is it's a lot harder on this selection because they can end up making things worse. But for a buck, you're usually pretty safe because your harmonics aren't going to be crazy high. So you're not going to get the X component dropping too soon because we're looking at what it starts losing out on the X at what 10, 20, 30, 40, 50 megahertz. So that would be the 50th harmonic, which normally doesn't become a huge issue. But yeah, let's just go with this Borns. I've had good luck with them in the past, and it doesn't have a huge drop off either. So, or I'm not even linking those, so we can just stick with that. So now on the input side, what I am going to do is just steal these from the last one, which I showed. And also, if any of you guys haven't, or if you're more interested in some of the simulation side with doing a pi filter and all of that, look at the USB hub series. I forget which video. Whenever I did the input filter, I think it was the last video, not live stream, that I did. I go into pretty good detail, and these capacitors, these 22 mics, are pretty awesome. Oh, but what voltage are they? 25 volts. That's cutting it a little close. So having a ceramic here helps with high frequency, the bulk capacitance, the electrolytic helps with our bulk capacitance, which, since we're not using a pi filter, doesn't have to be crazy. They're saying 68 microfarad. Probably go with 100 since they've been a little sketchy so far. So we can go with here. And notice how I'm still doing a pi filter. You still normally want to do that because it is still an inductive-ish element, so it's always going to help out. And you can add one sec. PC. Yeah, and you can add multiple of these if you want. You wouldn't want to add like 100 nanofarad or one mic, something like that, because you get that anti-resonance peak I'm talking about. The bigger the difference between them, the worse it becomes. So the big thing, back to the ferrite. Ferrites are fine for something like this, to where you know the frequencies aren't going to be crazy high, or you can know that they're kind of controllable. They become a little sketchy when you have like a bunch of different frequencies smearing together, and you might get really high harmonics. They can make things worse. But for something like this at 1 megahertz, it should be fine. Okay, so now let's do our input. And I guess we can do, since nominally this is going to be 5 volts, and then the input side, we can make it nominally 12 volts. All right, so is that, I guess that's roughly this schematic fleshed out. So then, if no one has any other thoughts or questions there, now what do we want to do with onboard LEDs? We could have a LED for input power, output power. We could do it for P good, but that would require us to have a FET drive, because we don't know how much this can sync. Or we could have it, I guess that's probably it, unless we did like a PFET on the input to do reverse polarity. We could show it on a reverse polarity hookup, but I think that's kind of excessive. But I'll just start doing the, because I'm pretty sure we'll probably want to have at least input and output, because I think that's what pretty much all eval boards have these days. So 5 volts, 220 should be fine. And on the input side, so now this is 12 volts, so let's do 510. You can simulate it on the same app, not on Vichet's. I mean, you can certainly simulate this on Spice or any of the other like full simulators. I mean, I don't think you can do it. On WeBench, you actually can do their input filters, but nothing crazy. Okay, so then really the only other thing would be to do the P good side, but I think we're fine with that for now. Oh, annotate. Oh, angry. Oh yeah, we need our connectors. So what are we doing connectors? Just a on KiCad? Oh, their simulator isn't really good. And plus you'd have to import it for each part specifically. I mean, I say it's not good. I have never tried it, and I haven't really heard much or people doing it, so I'm kind of assuming it's not that full featured, but I could always be wrong. Okay, so we have our kind of weird. The data sheet shows P good as a discrete. Yeah, that's what I was showing earlier. That they don't show actually what it can source, which or sync, which is kind of annoying. Because normally, like a P good, they say it's for usually driving an LED, so it's kind of weird that they wouldn't. As V out. So what is V out then? Wait, P good should be the same as V out present. I'm not following. Because this is completely separate from V out. So do you like import it? No. I would recreate what I'm actually simulating on here. I would not simulate this entire thing. All I would do is simulate the impedance and like a small AC signal analysis of the input filter. I wouldn't mess around with this. Oh, and it does this crap. So since these are all power outputs that can't be allowed, this is one thing I'd like for. I mean, I honestly don't know how they would actually solve it, but because you have a bunch of power outputs going into each other, I guess if you were to be able to put like a setting to where they're internally connected, that would do it, because then they're all tied together. So yes, they are all outputs, but they're tied together. So it's not actually bad. Okay, that's much better. Input power. Why are you angry? I know why that is. Oh, it's not labeled. Input power pin not driven. Yeah, that's fine. Okay, so now since the ferrite is a series element, it doesn't carry the 12 volts across, which is another thing I think KiCad could work on, is being able to let it pass through something like this if you explicitly tell it to. So then now we need a connector with. Do you guys want a single connector with the SDA or the I2C pins, the external voltage, and the P good all on one? Or would you want those to be separate? I just meant that the output voltage is present at the same time as P good, so separate LED. Oh, gotcha. Yeah. I can see that. That makes sense. Yeah, I haven't checked into the P good exactly, but yeah, I would assume they would be tied together. So if we did them all together, it'd be 1, 2, 3, 4, 5, 6 for ground. So I'll just start doing that and let me know if you don't like that idea. Oh, that's cool. Oh, bonus points for the developers. That's awesome. It shows you when it's in line. That's something I did not know. Oh, we have 1 vote for separate, 1 vote for all-in-one. Separate is simpler for users. Okay, so how do you want it separate then? And do you want... Yeah, how do you want it separate? So I2C, the 3 I2C pins with a ground, and then external voltage with ground. So a 4... Oh, and then what about P good? Yeah, you got to let me know how you want it separated. Yeah, that alignment is pretty freaking amazing. So these are all the pins that we need to have on a connector. And then ground. So 1, 2, 3, 4, 5, 6, yeah. Oh, and then obviously we'll need our output, but that's pretty self-explanatory. Anyone have any thoughts with the connectors? I mean, this, I guess this makes sense. So we would do those together and then P good separate. I just don't know how well this separates it out. Oh, are you guys thinking I'm talking about the output together? No, that's separate. I'm just talking about these pins. Because the problem is external voltage is used for both I squared C and P good because they're both pulled up to whatever you have here. This is what super chats are for. Biggest donations decide. Yeah, maybe one day I'll be there. Not now. Yeah, I'm used to single connector for logic. I think I'm gonna stick with that at least until someone tells me how else they want it. Because I think this totally makes sense. Speaking of the super whatever it's called, super chats, I recently set up a Patreon. I have the link in the video description if you're able to support on that. That is much appreciated. At least I think it's in the description. That and the Discord channel should be, which if you haven't joined the Discord, join that as well. One header. Okay, cool. So we're doing this. And now this S alert. What is S alert? What is S alert? How is that driven? S alert. S alert is something in a black box. So with the fuse question, I think JHON, is that pronounced John? Probably not. You had asked about the fuses. So if this was a board that I'm designing for a client, since S alert is some sort of output, that would get a fuse. SCL, SDA, depending, that would never leave a board if this was in a production product, but I would have some sort of caps on it, and there is a strict capacitance limit on the protocol just to help with some filtering. External voltage is drawn outside, so that wouldn't need a fuse. And P good, I would probably put a fuse on just in case. Yeah, the issue with what I was asking with the S alert is how does it drive it? Like, is it open drain? Like, oh, what do they say? Alert, yeah. Or if it's just a push pull, I don't really know. So that can be J2 and J3. And let me give me a second. Fuse or series resistor? Good question. I said fuse just because it's easier, because you don't have to think about the current limits, but it would depend. It would depend on how this was being used. You could certainly use this with a series resistor also. The good thing about a series resistor is it is idiot proof in the sense that it's resettable. So if you short something out, as long as you size the series resistor to where it clamps it to a current that the board can handle, you can just disconnect whatever was shorted and keep using it. The problem with a series resistor is you have to know exactly what this can drive and know how low the voltage is going to go with that. Where a fuse, at 250 milliamps, it's going to start popping. Obviously not going to pop it at that point. But that's another rabbit hole. Yeah, they make voltage drop. That's exactly what I was saying. You have to know what voltage drop and everything is allowable. All right, but I think that's a good spot to end today. So I'm putting this on GitHub. I just posted the link on Discord on the YouTube chat. So I'll push it right after this. Next video I'll do the calculations and stuff for the output caps, and then we can work on the layout. Definitely let me know any other changes you guys think when everyone has more time to look it over, or if there's any other thoughts you have with it. But otherwise, yeah, like I said, the Discord and Patreon links are in the video description. Please check them out, and I appreciate everybody tuning in. This definitely seemed like one of the more popular ones, and I appreciate all the support. Probably a stream next Saturday, I'm thinking, but I'll for sure let you guys know. All right, well, have a good one, guys. Have a good evening or early morning, depending on where you're actually at.